Okay, finishing up the position, velocity, and acceleration graph notes. We are given, for the fifth one, the first one on the back, a velocity. Using our questions that we developed to analyze graphs, we see that the velocity is negative the entire time. Okay, it's always below the x-axis. We also see that the velocity is not changing. The slope is constant. And what we can deduce from this is, since the velocity is negative, that means we're going to have a negative slope over here for the x versus t graph. Since the slope is 0, since there is no change to the velocity, we should have no acceleration, and that actually is probably easiest to do. We should have that for the entire time. So we can fill that in right now, no acceleration. Okay. It says to assume that x naught, the initial position, is 0, so we can put a line right there. Since we have a negative velocity and the slope of position versus time graph gives us the velocity, we should assume that we should have a negative slope, so we should have something going downward. Another way you could get to that is to say the area under the curve here is all negative, the area between the curve or the line and the x-axis. That area would be negative, therefore the area for velocity versus time graph is the change in displacement or change in position. If that's negative, then that means that the object is moving backwards. In other words, if it starts at 0, we should have an object that moves towards the negative, in the negative x direction. Okay, so all that being taken into account, we have a negative constant velocity. That means we should have a negative constant slope, perhaps something that looks like this. Now, I do want to make one little note. What if we had said that x naught is positive? How would that change everything? Notice that that wouldn't change the shape of the graph. That would just displace the graph farther up. Okay, up here somewhere, you would have a graph that looks like this. It would be the exact same shape, it just changes where the intercept is. If we said that x naught is negative, you would just be moving this whole shape down farther. Okay, so the initial position, the initial conditions don't change the shape of the graph, they just change where it starts and where the line goes. Okay, now what could this be? Let's do something really simple. This is just someone walking backwards at a constant speed, or at constant velocity, let's say. Okay, there we go. Let's move on to the second one. This is kind of a related shape to that one we had earlier with the bounce. It's not the exact same thing, but it's sort of similar, and maybe you'll see the similarity. For our x versus t graph, looking at this, we have a position or a displacement that is always positive, but does start and end at 0. So we have a displacement that goes up and then comes back down. Looking at the slope, kind of what we just said, we have a position that goes up and then back down. We have a positive slope, then a slope of 0 up here, and then a negative slope on the way back down. What that should correspond to is a very positive velocity right here, a velocity of 0 somewhere in the middle, and then a negative velocity ending up. If we start off positive velocity, then it crosses 0, no velocity, and then we have a negative velocity, you might guess that your velocity graph would look something like this, and you would be absolutely right. That's a little curved. Sorry about that. There, that's a little more straight. Okay. Again, positive, very steep upward positive slope here. Slope of position versus time means velocity. So that means we have a positive, a high positive velocity over here. That slope decreases towards 0, meaning we should have we have a slope of 0 here, which means we should have a velocity of 0 somewhere in the middle, and then after that point we have a negative slope, and an increasingly negative slope, meaning we should have an increasingly negative velocity. Looking at our v versus t graph, this shows us that this is a pretty constant line. Our velocity versus time graph, it has some positive spots, it's got some negative spots, but more importantly, it's got a negative slope. The velocity is decreasing the entire time, and that negative slope is constant. So the slope of velocity versus time is the acceleration. If our velocity versus time slope is negative and constant, our acceleration should be negative and constant. Okay, they're as constant as I can draw it. What motion is this? This is simply throwing something upward and having it be in free fall. So the part of this that's important is not the throwing something upward. That's not really included here. It's once the object is out of your hand or whatever, and it's in free fall. That's what's being shown here, okay? The throwing part is not there because that would not be the acceleration that we would get in free fall. There would be a whole different acceleration there. We've got two more to finish up. They're kind of similar. This is actually the reverse of one that we have already done, and this is a graph that you actually saw last year. So we're going to go through both of those. Looking for our first one, A versus T, we know that the area under the curve for acceleration versus time is equal to the change in velocity. We're told that the initial velocity is 0, and the area here in this first part of the graph would be negative because it's below the x-axis. So when you calculate this, we would get a negative area, which means the change in velocity must be negative there. In other words, the velocity should be decreasing. And if we have decreasing velocity from 0, we would have something like this. Okay? And that since that acceleration is constant, we know that the slope of our velocity versus time graph should be negative and constant, and it is. Then we have the opposite. We have a constant positive acceleration, which means we should have a constant positive slope on our v versus t graph. Another way of looking at it, the area under the curve this time would be positive, meaning a positive change in velocity. The velocity increases. There we go. And we get back to approximately 0. Now, if one of these was bigger than the other one, we wouldn't get back to 0. We'd either not get all the way back or we'd shoot past it. The fact that both of these areas are about the same means that if we start at 0, we're going to end up back at 0. Let's move to our x versus t graph. Okay? So for x versus t, we know that the slope of position versus time is equal to the velocity. We start off with a velocity that is 0, and then it becomes more and more negative until about halfway through. We know that x naught is positive to start. So we start off with a slope that's approximately 0, and then becomes more and more negative, like that. Okay, approximately like that. Then we reach a point where the velocity becomes more and more positive until it gets back to 0. Notice that the velocity is always negative, so our slope here should always be negative, except for the very beginning and the very end. And the area under our curve, the area between the curve and the x-axis, this would be negative. That means that we're losing displacement, and the displacement is becoming more negative. The position is becoming more negative. What this leads to is a graph that looks like this. We start off with a negative slope, and it becomes less negative as time goes on, till we get to a slope of approximately 0 again. So we have a graph that looks like this. You start off with a high position. You go backwards faster and faster with more and more negative velocity, and then you slow down. So perhaps this is someone that is accelerating backward from rest, and then braking to a stop. Okay. Last one. We have this kind of interesting stair-step pattern. We have an initial positive acceleration, then we have no acceleration, then we have a negative acceleration. The area under the curve means the change in velocity, so we should have a gain in velocity here, an increase in velocity. Since we start at, since v naught is 0, I'll put that dot there. We have an increase in velocity initially. Then we have no acceleration, which means that we shouldn't have any change in velocity. Remember, the slope of v versus t is the acceleration, so if the acceleration is 0, then we should have a slope of 0 here in this middle part, which basically just means a flat line. And then down here, we have an area that would be negative, which represents a loss of velocity, a decreasing velocity. And since our acceleration is negative and constant, the slope here should also be negative and constant. Notice that the velocity is positive the entire time this time, so that means we should have a gain in position, or a gain in displacement. The slope of position versus time is velocity, so since we have a velocity that is increasing and positive here, we should have an increasing and positive slope for our first part. This middle part is interesting. We have a constant positive velocity, which means we should have a constant positive slope, which would be this right here. Notice that it stopped curving upward. Now we're on a flat part, or a relatively flat part. The slope is relatively constant here. And then we have a decreasing but still positive velocity, meaning we should have a decreasing yet still positive slope. It should still be going upward, but the slope should be getting shallower and shallower until it gets back to 0. That might look something like this. Okay. There you go. The only thing that differentiates this from, I believe it was the last one on the previous page of notes, is that we have this extended part in the middle where there's constant velocity. And you have all experienced this motion yourself, and we did this last year as a lab, actually. These are the exact graphs that would happen if you were riding an elevator upward. How is that, you say? Well, in an elevator, you start off at rest. In order to start going upward, you have to have a positive acceleration to get yourself to go upward. In the middle of the trip, there is no acceleration because you're already up to speed. You don't need to move any faster. And at the bottom, at the end of the trip, in order to stop yourself at the floor that you're going to, you have positive velocity. You need a negative acceleration to slow yourself down. And if you look at this graph, that shows you how your position changes as you ride an elevator. You have an acceleration right here, then you're moving at constant velocity, then you have a negative acceleration, or the opposite acceleration here, to stop you. Okay? The more you look at these graphs, the easier they get to analyze. You should always be asking yourself those questions that I asked you to ask yourself from the other page of notes. You should always be asking yourself those. That's good prep for understanding, how these graphs work. And you should always be trying to remember as well the 10, maybe even less than 10 or so facts that that have to do with graphs. How to find position, velocity, and acceleration from any of the graphs that you might see, any of the different types, the position versus time graphs, velocity versus time graphs, acceleration versus time graphs. When I talk to you next, we'll be talking about vectors. Until then, have a great day.